Welcome to the Cognitive Systems Virtual User Group. This webcast will be recorded and will be made available for replay. A notice will be sent out to the participants when it is available. If you do not want to participate in this recorded webcast, please disconnect. The objective of the Cognitive Systems Virtual User Group is to share information and experiences with cognitive systems applications via regularly scheduled webcasts and replays. The target audience for this group is data scientists and other practitioners engaged in cognitive systems endeavors. The Cognitive Systems Virtual User Group topic areas include artificial intelligence, deep learning, machine learning, high-performance computing, open source databases, and other databases used in this arena. Our presenter today is Arnon Shimoni from SQream. Arnon will cover new approaches and solutions that are enabling full compute saturation with both GPU and CPU resources for high-throughput computations common in data science, business intelligence reporting, and ad hoc analytics workflows. Arnon will share how SQream's customers use a CPU-accelerated data warehouse to optimize the performance of advanced business queries without facing complexity at scale. Please submit questions via the WebEx Q&A panel. The questions will be addressed during the presentation, at the end of the presentation, or via an email follow-up. The presentation and link to the replay of this session will be posted to the website. When the material is ready, an email notice will be sent to all attendees. At this point, I would like to hand the webcast over to our presenter, Arnon Shimoni. Arnon, cheers.
Thank you, Victor. I hope everyone can see my screen. The title of this webcast is actually Effectively Analyzing Big Data with a Modern Data Warehouse. You'll see in a little bit why the GPU plays here at all. So without further ado, let's just head right in. So the first question is, what makes a company competitive? What we see and what a lot of our customers see recently is that in today's world, it's not enough to just, work based on hunches. And a lot of companies are increasingly data-driven. And we think that data is what makes a company competitive. This is especially true for kind of industries where the amount of data is really large and there isn't a big enough difference in the hard product. That could be a retail company, like a retailer with stores that may not be too different from other retailer stores, or it could be a telecom. So, for example, with telecoms, which is an area that we've had a lot of work in for SQream, is you get kind of the same product from every network. They all have the 4G LTE network, or sometimes even 5G today, but for the most part, it's kind of the same network. But what differentiates one company from the other is the ability of that company to adapt to customers, to kind of predict if a customer is going to leave them, to predict if a customer is getting good enough network performance, to offer that customer complementary products that actually are relevant to him, instead of just blasting out to the entire company, hey, there's a new kind of product available. So we think that companies become competitive with data. There is a lot of data being collected today. I don't need to tell you this. There's so many presentations out there where they show the graph of the data growing exponentially, and this and that amount of data is being collected every second. But that's just in general. But what we see is that a lot of companies are collecting more and more data internally. And they're doing that in order to analyze it, in order to make better business decisions. However, the infrastructure has not always kept up. This is something that was published on Forbes about a month ago. and I saw this article, and it's pretty much exactly what we think. The title of this article is "The Big Data Revolution Will Be Sampled: How Big Data Has Come to Mean Small Sampled Data." What we see today is that because of these infrastructure issues, because the data infrastructure has not necessarily kept up to date, the increase in data being collected means that less data is actually being analyzed in a percentage kind of calculation. So if a company had, let's say, 10 terabytes of data, and they analyzed 10% of that, they were looking at 1 terabyte, and that was fine. But if they're now collecting 100 terabytes of data, and they're still only looking at 1 terabyte of that data, it may not be a good enough representative sample. It's only 1% at this point. Now, if a company wants to be data-driven, looking at a very, very small subset of the data may not be enough to make good business decisions. Gartner actually says that about 60% of organizations' time is spent in preparing the data, which leaves very little time for actual analysis. Now, this is an actual problem that we see that is not necessarily due to the formats being saved, but it's an infrastructure issue. Data preparation tends to be because of the infrastructure selected. So the result of that is less than 10% of data on average being analyzed, and this is according to McKinsey. So we think there is a better way. What we're hearing from our customers is primarily, we only look at 10%, 20% of our data, but the biggest thing that I think here is this last sentence here. Existing systems are limited for current needs, will not scale, are costly, complicated, and require extensive support and maintenance staff. This is a really, really big problem. So back in the 90s, or actually in the late 80s, we saw MPPs starting to appear. MPPs are massively parallel processing systems, and they typically refer to a class of database or data warehouse like Teradata, like Netezza, like Oracle Exadata, these kinds of databases. Now, they actually gave a really big boost to enterprises to look at more data. They offered a very different approach to storing data and analyzing it by actually distributing the compute over many servers, many compute cores, and it got really, really good for customers, but as we know, data keeps growing. And as the data kept growing, these systems could not scale. They were very, very tightly integrated, and just adding more compute nodes is not something that they could do. So scaling for more users or scaling to more complex queries was really, really hard. So what companies ended up doing is replacing these data warehouses, replacing these tightly integrated pieces of hardware every few years. And that's it's just so incredibly expensive to do this, it kind of became unfeasible at some point. So MPPs actually tend to end up with a very complex architecture today. I mentioned 60% of the time, or Gartner mentioned, 60% of the time is being used for data preparation. And this is what it ends up looking like. You have data sources. These data sources can be flat files, they can be systems, they can be ERP, they can be other databases, but you have all these different data sources. These data sources go through some sort of preparation, cleansing, conversions, type conversions. The file has to be copied from one place to another, or you convert it from an XML to a CSV or whatever. And after that, they are loaded into a database, usually through an ETL process, but sometimes also directly. It's not necessarily loaded into the same database. It could be the same database, but it can be a bunch of different databases, each for a different kind of problem. We see today companies have, dozens and sometimes even, almost 100 different database products, each geared towards a different use case. But however, the data is not ready to be analyzed once it's loaded into the database. In most cases today, we see there has to be a process of compression, partitioning, indexing, pre-computations, cubing, projections, materialized views, each database with their own little, I almost want to call it a workaround. It's not actual workaround, it's more like an optimization where, you want to have the data readily available for the end user to query. Because if you just run a query against the database without doing all of these steps here at the end, the pre-computations, the projecting, the cubing, you're just going to wait a really long time for a query to finish, or it may just completely time out and kill your database server. So this is a fairly complex architecture, which is kind of limiting as well, because if you want to add another dimension to your query, you say, I'm actually interested in finding out and correlating my user base with maybe their location, but you hadn't planned this ahead of time. You have to talk to your DBA, you have to talk to IT, because there is significant overhead when you want to add additional materialized views or additional cubes. And this could take many months to actually get done in a large enterprise. You have to talk to the DBA, you have to talk to IT. In many companies, you actually have to file a whole bunch of forms, get them signed off on. And by the time that's actually done, you may not have the need for that data anymore. So the response time for this is extremely long. So we're looking at the year 2005-ish, and Hadoop starts to come in. And Hadoop is really designed for collecting large amounts of data of a variety of different data types and scale that really well. And Hadoop does that fantastically. What it's not designed for is analytics or any kind of SQL access. That's not to say companies haven't found a way to get Hadoop to respond to SQL queries. There are quite a few different SQL on Hadoop style solutions. But at its base, Hadoop is not designed for this. It's not designed, for example, to perform a join operation, which is the act of correlating data from different tables or different sources. It's not designed for high concurrent workloads. It's really designed for this MapReduce kind of operation, which of course has been split out at some point, and different products came in, but still Hadoop is not designed for analytics. So what most companies ended up doing is either keeping their traditional data warehouse or MPP solution, trying to work within the confines of the Hadoop world, or deploying a data warehouse alongside Hadoop. So Hadoop hasn't really solved the problems that a lot of people thought it would solve. And, Hadoop deployment can get messy as well. It's not a really trivial kind of product to deploy. Even with these more enterprise kind of solutions that bake a lot of the stuff in a single package, there's still a whole lot of stuff going on in Hadoop. And it's still a fairly messy ordeal. So our question was, when we started building our product, what if we could get faster analytics, but make it simpler to use and definitely simpler to manage? So that's where our product comes in. It's called SQreamDB. It's a GPU accelerated data warehouse. There are a few GPU accelerated databases on the market today. I'm sure you know some of them. I'm not going to say anything bad about them. They're all fantastic products in their own right. But we all kind of address a different need. So for SQreamDB, we are powered by GPUs, but we actually use the GPU not to speed a specific query. So we will not take a 2-second query and bring it down to 200 milliseconds. That's not what we do. We tend to focus more on high throughput compute, on analytic queries that require this high throughput compute, that, these queries that have to scan 50, 100, 150 terabytes in one go. So when we built our product, we designed it not to be limited by RAM. So if you have a machine with 96 gigabytes or 128 gigabytes of RAM, there's no problem to analyze 6, 10, 15 terabytes on that machine. We're actually designed for that. And that's where we really shine, where the data kind of tends to grow over the amount of RAM in a machine. Because if you have a machine with 1 terabyte of RAM, you can use an in-memory database to analyze 1 terabyte, and that's perfectly fine. And I recommend that you do that. It's going to be great. Once your data sets tend to be larger than the amount of memory you can stick in a machine, that's where we really shine. That's where the GPU and the other high throughput architectures that we have underneath, that's where they really shine. The other aspect to our database is the SQL part. We've built our own relational database. So SQreamDB is our own database. It's not a Postgres clone or a fork. It's not some other database. It's entirely homegrown. It is ANSI SQL compatible with a bunch of compatibility layers. So if you come from another database like Postgres or even Oracle or Microsoft SQL Server, you will be able to use SQreamDB pretty much immediately. There's a very minimal learning curve for that. And of course, we've designed it to be as fast as we can, primarily for high throughput compute. So we can do about 3 terabytes per hour per GPU. With more GPUs in the machine, you can do more loads and more queries and get additional concurrent workloads. So we're not positioning SQreamDB as a product that's designed to be the main operational database for a company. While we do have some customers who've done that, our main idea is actually to be like an offload database. So if you have heavy analytic workloads, you have really long queries, really messy kind of aggregations that you have to do, we are perfect for that. We're perfect for these ad hoc scenarios. You wouldn't want to run your operational database on SQreamDB just because there are better products who do that. And we're not really in that field. We're not optimized for that kind of use case. The fact that we've stuck to SQL and that we've stuck to the standards means that we work with ODBC, we work with JDBC. So on one hand, we have data sources coming in. It can be any data source, either directly or through an ETL tool. And on the other hand, you have the users, your BI users, your data analysts, your data scientists, and they're running whatever tool they want. They can run Tableau, they can run Spotfire, Click, they can write their own Python code in Jupyter, they can run TensorFlow, they may be using PHP to write a front end for some self-service BI. All of these just work through JDBC and ODBC, and it's standard SQL behind the scenes. So there's nothing really unusual for the end user about SQreamDB. It's kind of designed that way to eliminate the problem that I mentioned before, where you want to ask a question as a data scientist or as a data analyst, or you are the data user. You know the data better than anyone else, but you are limited because IT or your DBA said you can't run this query because we haven't thought about it ahead of time. So we're really focused on kind of bringing the control back to the data user, the person who knows the data best, and giving them maximum control over this. The only kind of weird thing about SQreamDB is that we have to have an NVIDIA GPU installed in the system. We like NVIDIA Tesla GPUs. They're the enterprise-grade GPUs from NVIDIA. When we actually started building our database, we didn't know if we could get enterprise-grade GPUs in rack-mount servers. Luckily, the industry has spoken, and we have GPU-enabled servers from everyone, from IBM through Dell, HP, Cisco, Supermicro, Lenovo, a bunch of other companies. They all do GPU-enabled hardware. And this is also true for the cloud. For Alibaba Cloud, which is a major SQream investor, for AWS, for Azure, for Bluemix, we have GPU offerings on all of those, and SQreamDB can and does run on those cloud offerings. So the key takeaway from this slide is it's usable by anyone. It sort of fits into your environment with kind of a minimal integration process. The main driver behind what we do is what we call high-throughput compute. Many of the discussions around GPUs tend to be about the number of cores that they have. So while it's true that the GPU has 5,000, this GPU specifically, the Tesla V100, has 5,120 cores, and it can do about 13 teraflops of floating point operations. It's actually the memory that's more interesting for us, because database operations tend to be kind of more memory bound, and getting almost 1 terabyte a second, so that's not terabit, that's 1 terabyte a second memory bandwidth from the GPU is a really important part of what we do. It's a key enabler for our algorithms, which are, all the database operations that run on the GPU. So it can be an order by for sorting the data. It can be a group by. It can be any number of mathematical functions that the database supports, which you know from other databases as well. But it's also the join operation. These operations are very, very intense in terms of memory bandwidth. And the GPU has, more memory bandwidth than any other CPU that we see today on the market, which really is a key enabler for what we do. So what does this look like? For a typical database to do data loading, you have your source data. And let's say that's 100 terabytes of data. You write it to disk, and then you can do some sort of compression on it, but you want to make sure that that will run fast enough. Because when you run a query, you don't want to spend too many CPU cycles decompressing that data, because that's going to be extremely time consuming. So you compress it with a relatively lightweight algorithm that will allow you to decompress it fast. However, as I mentioned, most databases don't let you just query a lot of data immediately. So if you have a table with 100 records, there's no problem just running any kind of query on that. But when you have 100 terabytes, running a query on that requires some sort of indexing, some sort of cubing, some sort of maybe materializing some views. That tends to add about 25% of the raw data size onto that storage. So you actually end up with more data than you bargained for just to run those queries. So as I said, the data may not be ready to be queried once it's done loading. You still have that intermediate process of preparing the data, which is what Gartner talks about, that 60% of time wasted. And I'll show you a case study of a company that we've helped, and you'll see exactly what I mean by that. So what we do is a little bit different. We actually load the data up to the GPU, and we compress it on the GPU. And we also collect a bunch of metadata on that raw data. So what we end up writing to disk is about a fifth of the data that was originally there. So our compression algorithms are a little bit more aggressive than what you might get with a CPU. That's because of the amount of cores, and that's because of the high memory bandwidth that we have with the GPU. So we're able to compress on average 1 to 4 to 1 to 5. That's on real world data. On synthetic data, it can get up to 1 to 22 and whatnot. And on really, really random data, it could be not really good at all. It could be, 1 to 2. But in general, we get about 1 to 4 to 1 to 5 on real world data. When we write that to disk, we're writing compressed data. Our additional metadata, which is known as, sometimes it's called zone maps, sometimes it's called a BRIN index. It's the same kind of concept. We collect ranges of the data, and we collect a bunch of other metadata about these small bits. It adds about a 1% overhead to disk. So you don't end up with 45 terabytes like you would if you had good compression on another database. You end up with 20.1. So it's only 100 gigabytes of extra data for the 100 terabytes raw data. The key thing to understand about our usage of GPU compression is it doesn't make you choose between having a good compression ratio or having performance. It's actually a key enabler in the performance because we want to save as much I/O as possible. If you read 1/5 of the data, you perform 1/5 less I/O operations, not just on the storage, but also on the network, also on the PCI Express or whatever other bus the GPU is on, and also you're performing less operations in the memory, which is crucial for getting high performance. So if you remember this diagram, and you should because it was just like 5 minutes ago, we have this complex process with MPPs. With SQreamDB, we can simplify that. So you will still have to ETL data in. You will still have to load data into SQreamDB in order to get good performance. But once the data is in, you don't have to have any intermediate steps for preparing the data or doing any kind of indexing. All of the previous steps that I showed you, the compression and the indexing, the transparent metadata that we collect is transparent by nature, and it's automatic, and it requires no user intervention. So that means the analyst or the data user can immediately run a query against SQreamDB when it's ready. This is something that we can only do by combining the high throughput architectures that we've talked about. I've mentioned that we don't see ourselves as a replacement for every database. We usually sit alongside an existing database or an existing data warehouse, and we tend to offload data for analytics, for ad hoc queries. So this is kind of where we see ourselves. This is most of our deployments. I've mentioned we have a few customers who have actually deployed SQreamDB as the operational data warehouse, but that's not the most common case. We have the ability to read data directly off a data lake if you have a CSV or a Parquet file, for example, stored there, but you don't get the same benefits that you would otherwise get if you stored the data inside SQreamDB. This is because we arrange the data a little bit differently on disk, and that's a pretty important part of our architecture. So with that, I'd actually like to show you what one of our customer scenarios looks like. We had a company contact us at Mobile World Congress a few years back, and that company is AIS. AIS is the largest mobile operator in Thailand with just under 41 million customers. And they said, we want to have a better product because these smaller companies are coming in and they have a lot more attention span for the customers, and they're offering them better products. They're targeting them a lot more aggressively. And we want to predict churn. We want to know what kind of network benefit they're getting. Are they maybe using a 3G phone on a 2G network, or are they maybe walking around my competitors' stores? I really want to know that so that I can target them a little bit better, which sounds a little bit sinister, but it actually makes sense because you want to offer your customers a better product, and you want to make sure they're getting the most for their money. So we were actually competing against an incumbent database. They had Greenplum deployed internally. Now, Greenplum is another columnar database. It is based on Postgres. It's a very, very good database. It's also designed for analytics, and we really like some of the stuff that they had done. But Greenplum does require a lot of data preparation. So this says ingest time, but it's ingest plus data prep time. So overnight, AIS would load data from their 3G, 4G, SMS, voice networks, and a bunch of other stuff, and they would prepare the data to be queried the next day. This process would take about 5 hours, plus 2 hours for the reports to be created. The problem was, this could take more than 7 hours combined. So this is 7 hours. On holidays, on days where people use their phone a little bit more, this process could take a little bit longer. It would take about 8 hours. When AIS employees showed up at 8 in the morning, they expected to have their data warehouse ready to answer questions. So any long-running process that had not yet finished would be killed. And then they would not have the necessary reports for that day. So they would be kind of working blind. We showed them that we can do the same thing in a lot less time. So our ingest time was just 20 minutes without the data preparation. As a reminder, we don't need this data preparation because we operate on raw data directly. They took their SQL query. It's actually not one SQL query. It's a bunch of SQL queries that kind of build up one on top of the other. They have a bunch of aggregations. They have a bunch of window functions and joins, and they're joining about 7 or 8 different tables together. And they ran it on SQreamDB. And this is my first deployment as a person who had moved from developing the product into doing kind of solution architecting. And I'm sitting there and they're running this query, which I've never seen before, and I have no idea if it will run. And it runs, and it takes, the clock starts ticking. And I know it's supposed to beat 2 hours, but I don't know if our product can do this. I've never seen it do this live. I've only seen it from being a developer. But it finishes in just under 10 minutes. I know this says 10 minutes, but it was actually 9 minutes and 40 seconds. And it finished, and they did not believe us. And to be completely honest, it's a scary thing. We're like this new vendor coming in, and we're showing them that what they have is really very slow. So what they do is they take the results and they put it in Excel, and they take the results from Greenplum and they put it in Excel, and they go cell by cell, and they check every single value. And once again, I don't blame them. I would have done the same. But we passed that test. And then they said, okay, we don't want to look at one day of data. We want to look at 11. So load that, and let's come back after lunch, and we'll see how that works. So we actually could run the query before lunch. During their lunchtime, we ran the query, and we saw that it actually finishes, once again, a lot quicker than what they had on Greenplum. Now, it's important to also compare the size of the solution, because their Greenplum was 80 nodes with 7,600 logical CPU cores. And our solution was a reused server. We actually asked for a different server, and they said, this is what we have, take it or leave it. And we took it. And we had 96 gigabytes of RAM on our server. And we were looking at about 6 terabytes of uncompressed storage, which was, it's a decent amount for a single server. But we only had one GPU in there, so we couldn't actually run anything a lot more complex than what we had already run. Luckily, this project converted into a very successful project, and they've deployed it, and they've actually expanded it a couple of times now, which we're really very proud of. I do want to show you what the sample dashboard we generated looks like. So this table aggregates directly off SQreamDB. And what it does is it shows the throughput of data across a variety of different customer types, and it's grouped to different times of the day so that they can see what kind of data throughput you're getting in the morning, in the lunch, while everyone is sleeping for specific customer scenarios. So they're actually looking at what do Samsung users who are of gold or platinum quality get in Bangkok on these specific dates. So that wasn't an easy query, and this is running live off Tableau. It's not some sort of extract or some sort of pre-aggregated table. It's running directly off SQreamDB. And they were really very happy with that. You could see their eyes widen up with the opportunity to run more queries. They had to sit there in the meeting room and, step by step go through all different types of customers and tourists and prepaid SIMs and whatnot. So it was really very, very interesting for me as well. I want to show you the architecture before and after because I think this is kind of interesting. Without SQreamDB, we had all the 3G, 4G, CDRs, voice, SMS stuff coming in. It would take about 2 hours to ETL that into Greenplum, and it would take another 3 hours to actually run the daily aggregations to create the reports the next day. So this process takes about 5 hours, and this process for the daily reports would take about 2 hours every day. They also had 7 days of compute time that they would allocate just for monthly reports. These reports are varied. They work for different parts of the organization. Some are for marketing, some are for infrastructure, some are for the network part. The fastest report that they had would take about 30 minutes to run, and the slowest report would take about 5 hours. With SQreamDB, the rest of the project was actually to run all of the monthly reports. We took their entire monthly report from 7 days down to 1 day. The fastest report went down from half an hour down to 2 minutes, and the slowest report went down from 5 hours down to 10 minutes. ETL process was about 25 minutes per day together. Now this can be parallelized. You can do this actually in 20 minutes flat, but we can say 25 minutes just to be conservative. This is the kind of stuff that SQreamDB does. I mentioned it's designed for high throughput calculations. It's not designed to answer a single, where is this customer's address? It's designed to look at trends. It's designed to look at really large collections of data and give back reports in what we call human real time. So it's not real time. It's not 200 milliseconds. It is what we call human real time, where at worst you go out to your lunch break, and when you come back, you have your results. I would say in most cases, it's typically a coffee break or even a short bathroom break. So that's kind of what we do. I do want to show you one more thing because this is quite important. We've recently partnered with IBM to get more of out of our system. So SQreamDB is entirely software. It's just a software solution. We don't sell the hardware. We only recommend what kind of hardware we like, but we don't sell the hardware. We sell our software and professional services, typically through channels or through partners. With IBM, there's actually Power9 with NVLink. Now, NVLink is a different bus. It replaces the PCI Express bus so that the GPUs, instead of sitting on the PCI Express bus, which can do about 32 gigabytes bidirectional, gigabytes a second, we use NVLink. Now, NVLink is a bus that was developed jointly by IBM and NVIDIA in order to kind of bypass this limitation of the PCI Express. And we get about 300 gigabytes a second on NVLink, which is almost 10 times more than PCI Express 3.0. What that means is we're able to push more data into the GPU. I've mentioned the GPU is an extremely capable piece of hardware, but it's only as capable as the bandwidth that leads up to it. Because if we can only get X amount of data into it, we can't do 3x performance. So IBM with Power9 on the AC922 and NVIDIA with the Tesla V100 is a really incredible combination. I mentioned the bandwidth, and I mentioned that it's not just cores. I've already talked about this. But we're getting 300 gigabytes bidirectional on the Power 9 CPU, and we're getting 900 gigabytes a second inside the V100, which is an incredible amount of power. Now, what does that look like, you're asking? I'm glad you guys asked. I know you didn't, but I'm going to tell you anyway. On Power 9, without changing any piece of the puzzle, on a comparable Intel server, we can load the entire TPCH data set in about 1,900 seconds for 6 billion records. On the IBM Power 9, we can do this in just about half of the time, so almost 1,100 seconds. It's 1.7 times faster, and we didn't change a single thing. Same storage, same amount of RAM, same GPUs. The only difference is the IBM Power 9's processor and the NVLink bus between the CPU and the GPU. Now, I know some of you may have heard that there are other computers that have, other servers that have NVLink. Typically, that NVLink is only between the GPUs themselves. Intel servers do not have the CPU to GPU NVLink bus. This is unique to IBM, which is why we were really excited to actually port our software over to SQreamDB, to Power 9. And this is starting with SQreamDB 3.0, which we released late last year. Now, it's not just faster for data loading, it's actually also faster for querying. So TPCH query 8, which is a query that also is a little bit of a random IO type query that reads a lot of data and actually writes a little bit of data back to the storage, was 3.7 times faster. It went down from just under a minute on Intel to just under a quarter of a minute on IBM Power 9. And once again, we did not have to change a single thing. It's the same software, just running on different hardware. So we're really pleased with this. These are fantastic results. And we've actually recently announced, earlier last week, we announced our latest customer, another telecom actually, LG U+ in South Korea. They've deployed SQreamDB on IBM Power 9. They're our first production IBM Power 9 customer, and IBM storage as well. So it's a really fantastic deal, both for IBM and for us, and for LG U+. And they're actually doing a similar scenario to what AIS are using SQreamDB for. They're doing CDR analytics, and they're doing network health, and they're looking to really understand how they can optimize the network further by looking at more data. With that, I'm right about done. So I'm ready for questions if you have any. I'm not sure I've seen any so far. Victor, have you seen any questions come in?
I have not seen any questions there. I had one question myself. You were showing in one of the earlier slides all of the various things can operate with the SQream database. I didn't see Spark in the list. Does Spark work with it?
Are you talking about this slide?
Yes.
Spark is right here on the top left. So yes, we do have a Spark connector.
Okay.
But you can also use Spark via JDBC or.
I was looking at the right side, not the left side.
Okay. We don't actually. We haven't tried getting data from SQreamDB into Spark. It's not a use case that we've come across. We've seen cases where Spark does some sort of stream analytics, and then it provides a more complete data set. It can be used, for example, for enrichment of data, and then we pipe it into SQreamDB for analytics. That's something that we've seen a few times already.
Yeah, and I had another question about real time. I think you addressed it as you went through after it had occurred to me. But you don't really do this streaming. You do what you called human real time.
Correct. So it's a really different kind of problem, right? You can do really, really fast analytics if you have enough RAM. You can do real time. You can use a real time database or an in-memory database if you have enough RAM. The problem with that tends to be the scale at some point. If you're looking at more than 30, 40, 50 terabytes, scaling in-memory databases tends to be really expensive. And that's something that we don't really address today. It could be that in the future we will be stepping more into the real-time kind of use cases, but right now we're focused on really on the high throughput. We see that as more of a low-hanging fruit, so to speak. It's something that a lot of data warehouses, both MPP and non-MPP, have kind of neglected. Same goes for a lot of the Hadoop stuff. It's just not addressing the issue of high throughput compute really well. So that's kind of where our offering sits. That's where we target ourselves right now.
Thanks to our previous side conversations, I actually know the answer to this, but we've got a question in the window. Can you see it, or should I read it?
Let me just figure out if I can see it.
Can SQream be used for unstructured data, or is this primarily for structured data?
Oh, yeah, I see it now. The answer is it's primarily for structured data. We organize the data on disk in a very specific way. So right now, the answer is strictly structured data, or if you're doing some sort of text analysis, we can do some of that. It's worth noting the GPU is not ideal for unstructured data. It tends to kind of diverge a lot, and if the operation can't be very repetitive in nature, which you get with structured data, then the performance tends to decrease. So right now we've not addressed that too much. It is in our roadmap for later this year to add more unstructured data support. What we do right now for customers that do have unstructured data or semi-structured data is we convert it on ingest. So we use either a custom parser or Talend or Informatica or DataStage to do the conversion into a relational structured format.
Okay. Another question that occurred to me as you were going through, and I think I heard it answered at least by indirect reference. So I think I know the answer to this, but is SQream a columnar database?
Oh, yes, it is. It's a columnar database. We store our data it's our own proprietary format, which predates other columnar formats like Apache Arrow or Apache Parquet, but it's very, very similar in nature. Ours is actually splits the metadata to a different location, so we're actually able to read whatever part of the data we want, which you can't really do very well with Parquet. With Parquet, all the metadata is at the end of the file. You have to seek for that. So it's our own proprietary columnar format. It's not a secret. It's just proprietary. Yes, so it is a columnar database. It's really important, as I mentioned, for GPUs to work on structured data. And columnar databases are even more structured because you have a column of a specific type that doesn't really change. So you don't have an integer turning into a string, turning into a date or something like that. So when you're loading columns into the database, you're really using the GPU to its fuller extent, so to speak. You're letting it be more predictable.
And focusing on the slide that's up right now, being an SQL database, almost anything can interact and use the data that would use an SQL database. Is that true?
Yeah, as long as it supports ODBC or JDBC, or it can use the Python DB API, then yes, pretty much any tool can use it. We really like.
Okay. We've got another question in here. What's the average time frame to conduct a POC that you've experienced?
Days, sort of work that we do internally to optimize it further, but yeah.
I'm not sure if we overlapped each other there, Arnon.
Maybe.
There's a question in the window. What's the average time frame to conduct a POC that you've experienced? Days, weeks, or months?
I would want to say days because that's the amount of time we typically spend on site with a customer. We do a bunch of preparation work ahead of time. So we will, of course, like to fully understand the use case so that we can know if the database is a good fit or not. I've mentioned that companies can have tens or sometimes even hundreds of different databases. Every database is kind of good for another use case. And we want to make sure that the customer does not think, for example, that we would be a good replacement for their Hadoop system entirely or for their Oracle in its entirety. So we do some sort of work with the customer where we do the discovery, we find out what the requirements are. We may even opt to do some internal testing in our lab where we give the customer the opportunity to load either dummy data or their own data into a SQreamDB instance running in our lab. And then they can verify if that's good or not for them, and they can see the performance. When we actually do the implementation, it depends on the infrastructure. If it's AWS, we can do, from launch to handover of the system in a week, in like 5 days. If it's on-prem, typically they have to acquire the hardware. Not every company has an NVIDIA GPU available. Some do. If they already have the hardware available, it's really a matter of a few days. You copy over the SQL statements from the other database. So you create the tables, you do the data load. I mentioned we do about 3 terabytes an hour. So even if you're looking at copying 100 terabytes, it's not going to take more than a few days to load the entire data set into SQreamDB. And then it's immediately ready to run the queries. Now, the queries might need some changes. For example, if you're used to datetime 2 on Microsoft SQL Server, while that will work, we recommend that you use, datetime instead of datetime 2. If you're used to using the Oracle decode function, maybe you will want to use another function that works better in SQreamDB. So there are some changes. We tend to stick a little bit more to the ANSI standard, and for what ANSI doesn't cover, we stick to Postgres. But so to summarize, it would be the entire engagement would be a few weeks. On-site, it would be a few days from start to handover.
Thank you. Any other questions?
There was a question about, there's another question. What kind of industries does SQreamDB work in? So you've seen it from me. There's a lot of success in telecoms. Telecoms tend to be a little bit more forward-thinking, and they're more sensitive to collecting lots of data and analyzing it because of that competitiveness. So we've had a lot of success in telecoms. We work with I think 5 different telecoms at this point. But there's also there are also a few use cases in retail research, and actual retail resellers and warehouses and that kind. There are some things we've done with finance and some things we've done with cybersecurity, primarily along the lines of risk and fraud detection. So those are the most common industries we work in. We also have a deployment we did for Sheba Medical Institute, which is a big medical research institute in Israel, where they have 2 researchers doing DNA comparisons against a whole bunch of different samples from a person's genetic group. And there are 2 researchers with 1 petabyte of storage behind the scenes. So it's a single SQreamDB server with 1 petabyte of storage behind the scenes, and they've cut down the research time from months down to a few hours, which is really, really critical when you're waiting for a screen to tell you if you are at risk for a specific type of cancer, if you have the specific mutations in your DNA. Waiting months is extremely painful compared to waiting just a few hours. So that's a use case we're really proud of. But that's the only thing we have in Genome right now, unfortunately.
Okay, apparently that last question went directly to you and not into the all panel. So
okay.
Do you have any others there coming to you privately?
That's the only thing I saw. Yeah.
Okay. All right. Just giving it another moment or two. Does anyone have any additional questions for Arnon today? not seeing anything additional, Arnon, so
there was a question about, is the slide deck available to download?
Yep.
We'll make it available.
I will take care of all of that. Arnon will get me the presentation. There will be a replay from the recording as well, and you will all get an email with those links and information in order to get to that.
All right, fantastic.
Okay.
So thank you very much for the opportunity today.
Thank you, Arnon. It was very informative. I appreciated it a lot. I particularly appreciated the education up front about the journal methods that are used in the industry today and how SQream can be applied to that and improve those situations quite substantially by using GPUs. But thank you very much. I appreciate that.
No problem. Happy to always happy to talk about this topic, which is really close to my heart, having been a database user who suffered from some of this stuff before. So once again, thank you very much for the opportunity. And by the way, you're free to check out our website. A lot of the information is up there. We have brochures and whatnot available for download. So that's SQream.com. Really easy.
Okay. Thank you. I'll do my closing now. Thank you for joining the call today. The presentation and the link to the replay of this session will be posted to the website. When the material is ready, an email notice will be sent to all attendees. The plan is to have additional presentations on the second Tuesday of each month at this hour. As you exit the WebEx today, you should be presented with a survey in which you will rate this presentation and indicate if you would like to be notified of future presentations. The supporting infrastructure for this group includes WebEx used for the webcasts, a website where presentation and replays will be posted, and a LinkedIn group which will be one avenue for notices. Information on these will be included in the notices that you receive. Please join the LinkedIn group to ensure that you receive future notices. Thank you. You can disconnect at this time.